In today's lecture, we will be discussing on closures of a relation. Now, suppose I have a set A and a relation R on the set A. That is, R is a subset of A cross A. Now, we have already seen that relations satisfy certain properties like reflexivity, symmetry, transitivity, antisymmetry and so on. So, we will be particularly discussing on three properties: reflexive, symmetric and transitive. So, reflexive, symmetric and transitive properties. However, to start with, we will just take a general property, let us say P, that is, let us denote the property by P. Suppose P is a property of a relation. In particular, P can be, as I said, reflexive, symmetric or transitive property. Now, a general relation R may or may not have P. So, that is our starting point. So, suppose we are considering a relation which does not have the property P, then we may ask that I would like to extend the relation to a relation and this extension should be minimal such that the extended relation has the property P. For example, if the property is reflexivity, or let us say reflexive property, and suppose R is my relation which is not reflexive, I would like to extend R to a relation, let us say R sub P, such that R sub P is reflexive and it is the smallest reflexive relation containing R. Now, in general, let us give a definition with respect to the general property P and a general relation R. The closure of a relation R on a set A, the closure of a relation R on a set A with respect to a property P, say, is the smallest relation denoted by R P such that R is a subset of R P, which in turn of course is a subset of A cross A. Now, here there are certain issues that needs clarification. First of all, the point which is more or less clear, that what we mean by a relation containing another relation, because after all we have defined a relation to be a subset of A cross A on which it is defined, and then if I say that the relation R P is contained in R, that means R is a subset of R P as a set. But a more critical point is that this R P has to be minimal with respect to the property. The question is, what do we mean by that? We are coming to it shortly, but let us write again the same thing more explicitly. So, suppose R P is the closure of R with respect to P, then what are the properties that R P must have? In other words, suppose R P is the closure of R with respect to the property P, then 1, the first thing is that R P must have the property P. Then second, R must be a subset of R P, which in turn is a subset of A cross A. And third, if we consider a relation S with property P containing R, then and contained in R P, then S must be equal to R P. If S is a subset of A cross A having property P, and R is a subset of S, which in turn is a subset of R P, which in turn is a subset of A cross A, of course, then S must be equal to R P. And the third point specifically say what we mean by the minimal extension. It means that we have a relation R here, and then we have A cross A, and R P is somewhere in between, such that R is a subset of R P and R P is a subset of A cross A. It is to be remembered that R P satisfies the property P. Now, suppose we have some S which also satisfies the property P and which is a superset of R as I have drawn here and subset of R P, then this will force S to be equal to R P. So, that means that we have R, the relation R over here and R P on the top of it, and which satisfies P, but there is no relation in between R and R P satisfying P and properly contained in R P. So, R P in that sense is the minimal extension of R having property P. Now, we will start looking at closures of specific relations, that is closures of relations with specific properties. The first property and probably the easiest property that we have in hand is reflexivity. So, we consider now reflexive closure of a relation. Suppose R is a relation on A, the reflexive closure of R is a relation R C, say such that R C is reflexive and suppose S is any reflexive relation such that R is a subset of S, which in turn is a subset of R C, which in turn is a subset of A cross A, then S equal to R C. Thus, we see that this is exact translation of the general case that we have discussed just some time back, considering a general property. Now, the property is no more general, this is the reflexivity property, and we have said what we mean by reflexive closure of a relation. Now, we ask the question how to find the reflexive closure of a relation. The reflexive closure of a relation R on A. So, let us be very specific that we have said, suppose A is the is the set on which relation R is defined, and we would like to know the reflexive closure. And of course, if R is reflexive, the reflexive closure of R is R itself, but we do not know that. Therefore, we define a relation which we denote by capital delta, and which is essentially the equality relation. So, capital delta consists of all points A such that A belongs to A, or in other words I can write it contains all pairs A B such that A comma B belongs to A and A equal to B. All right. So, this is the equality relation. Now, what we do is that we simply augment, if at all necessary, these A type of elements to R, and we call that is R C, that is the reflexive closure of a the reflexive closure of R. And I do not think I need to explain anything more, because it is very straightforward. R C is equal to R union capital delta, the equality relation. Now, suppose we are given R in terms of a matrix, that is, instead of R we are given the matrix corresponding to R, that is MR, and then it is very direct that the equality relation is nothing but the identity matrix. All right. So, only the diagonal elements will be 1 and rest will be zeros. So, we are assuming here that A is of size n. All right. So, delta is this thing, the identity matrix, and MR of course is a matrix, is the matrix corresponding to R. And if we want to know the matrix corresponding to RC, so that is MRC, we can just write this is equal to MR union delta, because we have already told that RC is R union delta, and we know that from our previous lecture that this is equal to MR or M delta, and M delta essentially is the identity matrix. Therefore, this is MR or IN, where IN is equal to the n by n identity matrix. All right. So, this is easy, but well, this somehow captures the basic idea of closure, that we just add new elements to the relation, original relation R, to maximally extend it to its closure with respect to certain property. And we have also seen here that if we write in terms of matrices, sometimes it is possible to write the whole computation very neatly, because we just know now that we have to just take the OR of the identity matrix to the original matrix of the relation, and the matrix that we get is the matrix corresponding to the closure. Now, let us look at an example. Right. Now, let us consider A to be the set 1, 2, 3 and 4, and we consider a relation R equal to say 1 1, then 1 2, 2 3 and 3 4.
Link it.
Link. Not linking. Huh?
This one is the link.
This is the link.
Yeah.
I am doing it, but
now
it will come.
It's okay now.
Okay. So, I have to press here. It was not happening actually when I pressed there, but it was not happening, but anyway. All right. So, this is 3 4. Okay. Now, suppose we want to find out the reflexive closure of R. Well, then we have to write down the equality relation, which is very straightforward because it is 1 1 2 2, then 3 3 and then 4 4. Four, 4. All right. Now, we take R union delta. This gives us 1 1 and then 1 2 and then 2 2, then 2 3, then 3 3, 3 4 and lastly we have 4 4. Of course, this is the reflexive closure. If we now look at the graph corresponding to this relation, then we will see that we have another way of looking into the reflexive closure. So, let us look at the graph corresponding to R defined on A. So, we have got 4 vertices, we label them by 1, 2, 3 and 4, and here we notice that 1 1 is there. 1 1 means there is a self loop from 1 to 1, and then we have an edge from 1 to 2, and then we have an edge from 2 to 3, and then we have 3 to 4. This is the original relation given by R, and finding out its reflexive closure is just putting self loops at each vertex. That makes each of the vertex related to itself, and where there is already a self loop, that is in this case 1, we do not have to do anything. So, this is the reflexive closure of the relation and a relation R and the graph corresponding to it. All right. Again we start with R. Suppose R is a relation on a set A, the symmetric closure RS of R is a symmetric relation containing R, is a symmetric relation containing R such that if S is another symmetric relation satisfying R subset of S subset of R S subset of A cross A, then S equal to R S. Now, we come to the question of how to find the symmetric closure of R. In order to do that, we will first start by defining another relation corresponding to R, which is called the inverse of R. We denote it by R inverse and define as A R inverse B if and only if B R A. Now, at this point we must not confuse R inverse with complement of R. Since R is a subset of A cross A, there is a set theoretic complement of R which we usually denote by R overline, which is essentially A cross A set minus R. Now, when we translate it in the language of relations, this will mean that A R complement B if and only if A is not related to B. This is our complement, but we are not here defining complement of R, we are defining R inverse, where we say that A is related to B if B by R inverse if B is related to A by R. Now, what we claim over here is that the symmetric closure of a relation R that we are denoting as R sub S is nothing but R union R inverse. Now, we have to see why it is true. So, first we have to show that R sub S is symmetric. For that, let A R sub S be. Now, this implies that A R union R inverse B, which implies that A R B or A R inverse B, which in turn implies that B R inverse A. Well, that is the definition of R inverse. We have said that A R B if and only if A R in B R inverse A. So, since here we have got A R B here, therefore, I can write B R inverse A. Since A R inverse B if and only if B R A. Now, or B R A. Therefore, we see that this is B R A or B R inverse A, but that means that B is R union R inverse A, which in turn means B R S A, because R S is R union R inverse. Therefore, we see that A R sub S B implies B R sub S A, but that is the property that R S has to have if it is symmetric, and so R S is symmetric. The next property that we have to show is that R is a subset of R s, but that is extremely straightforward over here because R s is union of R and R inverse, and therefore, we can write that R is a subset of R union R inverse, which is equal to R s. Now, we come to the third property, which is the minimality. So, now let us suppose that we have a relation, let us call it T, which is symmetric and which is sandwiched between R and T. So, suppose T is a symmetric relation on A such that R is a subset of T, which in turn is a subset of R s, which of course is a subset of A cross A. Now, let us start from let us try to prove that T is equal to R s. We already know that T is a subset of R s. Clearly, T is a subset of R s. We have to prove the other way around. So, we start it in a fresh page, right. So, let us write again. So, we have R a subset of T, which in turn is a subset of R s. Of course, T is a subset of R s, it is already known. Now, I will start from R s side. So, suppose that A is related to B by R s. Now, this implies that A is related to B by R, or A is related to B by R inverse. This is because R s is a subset of R union R inverse. Now, this implies that A is related to B, that is all right, or B is related to A, okay, because that is by the definition of R inverse. We know that A R inverse B both B implies B R A. So, therefore, we can write that A S B or B S A. Why? Since R is a subset of T. So, just let me correct, this is not S, but this is T. So, instead of S there, I must write this is T, because since R is a subset of T, A R B means A T B, B R A means B T A. Therefore, we have come to a scenario where A is related to B or B is related to A. So, therefore, through R, therefore, since R is a subset of T, I can say that A is related to B by T, because it is related to B by R and R is a subset of T, and or B is related to A by T. Now, we started with the assumption that T is symmetric. Starting assumption is that T is symmetric. Okay. So, therefore, A T B or A T B, here this thing B T A is A T B because T is symmetric, and therefore, we have the same thing, we have A T B or A T B. Therefore, this implies that A T B. Now, this means if we now notice from the beginning, that is this, to the end, we have proved that A R sub S T implies A T B. This implies that R S is a subset of T, but already we knew that T is a subset of R S. Now, we have got R S is a subset of T. Therefore, we have T is equal to R S. So, this is what we wanted to show to prove the minimality of R S, and this is what we have shown. Now, we will consider the matrix corresponding to R S. So, in general we will consider matrix corresponding to a what we want to consider now is how to construct the matrix corresponding to R S. So, first we have to know how to construct the matrix corresponding to R inverse. Now, if you see that a matrix M R which corresponds to the relation R defined on A is given by Mij n cross n, where the number of elements in A is n on which R is defined, and further to specify the matrix we need to write the elements of A in some order which we fix afterwards. So, suppose when we write in that order the elements of A is A1 up to A n, then Mij is equal to 1 if Ai is related to Aj, is 0 if Ai is not related to Aj. Now, suppose we consider the matrix corresponding to MR inverse. Now, suppose we denote this matrix by Mij bar, sorry Mij prime. Now, Mij prime is defined in this way: Mij prime is equal to 1 if Ai is R inverse Aj, that implies Aj R Ai, and 0 if Ai is not R inverse Aj, which implies both ways if Aj is not related to Ai. That means that M prime sub ij equal to M j I, because when Aj is related to Ai, then M sub j I is equal to 1. Well, then M prime sub I j is 1. Therefore, this relation holds, and when j is Aj is not related to Ai, then M j I is 0 and same as M prime sub I j. Therefore, this is same. Thus, it is clear from this that M sub R inverse, that is the matrix corresponding to R inverse, is equal to the transpose of the matrix corresponding to R, because in the new matrix the I j is switched, that means rows and columns are switched. Therefore, we have this, and now since we know that R s is equal to R union R inverse, the matrix corresponding to R s is the matrix corresponding to R union R inverse, which is equal to the matrix corresponding to R or the matrix corresponding to R inverse, which in turn is equal to the matrix corresponding to R or the matrix corresponding to R transpose. This gives a particularly straightforward method to construct the matrix corresponding to the symmetric closure of any relation, and then of course, from that we can write the relation or the digraph corresponding to the relation very quickly. Next, we come to the question of finding the transitive closure of a relation. The transitive closure of a relation is a relation which is transitive and which admits no transitive relation between itself and the relation under consideration. So, transitive closure of R on A is a relation. We usually define transitive closure as R superscript plus. I will read it as R plus is a relation R plus such that R plus is transitive and any relation T on A which is transitive and R subset T subset R plus, of course, all subset of A Cartesian product A is equal to R plus, that is T is equal to R plus. So, again we have the problem of finding out the transitive closure of a relation. To do that, we have to recall few things that we have studied in previous lectures. So, if we have a relation R, then we can take we can compose this relation R to with itself several times. For example, by R square we mean the relation R composition R. Now, when we say that an element A is R square B, this means that there exists an intermediate element C 1, let us say in the set A on which R is defined, such that A R C 1 and C 1 R B. Now, suppose we raise R to the power 3, then A R cube B will mean that there are elements C 1 and C 2 belonging to A such that A R C 1, C 1 R C 2 and C 2 R B. If we go forward like this, then we can define the general case, that is, let us say A R to the power k B, all right. This means that there exists C 1, C 2, so on up to C k minus 1 belonging to A such that A R C 1 comma C 1 R C 2 so on C k minus 2 R C k minus 1, then C k minus 1 R B. So, we see that we can have sequence of powers of R defined in this way, that is R square, R cube, so on, R k and so on. We can construct a relation by taking the union of all these relations. So, we consider the relation that we get by taking R union R square union R cube union moving in this way R k union so on. In a compact way, we can write this as I equal to 1 to infinity R raised to the power I, and what can be proved is that this is same as R plus, that is the transitive closure of R. We will stop here in today's lecture, and we will continue discussions on closure of relations, particularly closures, particularly the closure of transitive relations in the next lecture. Thank you.